Hello there, my name is William Iliff. I'm a fourth year DPhil student working out of Oxford University's Materials Department. My aim today is to tell you a bit about my work to build an experiment to allow me to simultaneously ion irradiate and test the critical current of REBCO coated conductor samples and thus provide a decent comparison with some of the excellent work that's gone before me, trying to judge how REBCO coated conductors will fare in future fusion applications. So what I'm just trying to represent here is the crux of the problem when designing a magnetic confinement fusion device. Now these devices want to contain and control a hot fusion plasma using magnetic fields, but the high energy neutrons emitted by the DT fusion get everywhere and essentially limit the lifespan of every aspect of the device, including the very magnets built to contain the plasma. Now, there's a lot of good work that's been done to aid the design in all of these elements, but my project concerns whether REBCO coated conductors are a good choice as the superconducting current carrier for these magnets, considering they will be being neutron irradiated whilst carrying their rated current and at their operating temperature and subject to magnetic fields. Now, much of the work judging REBCO's capabilities up till now has involved radiating at room temperature or higher. So the aim of my work was to get just a little bit closer to the actual operating conditions by irradiating and testing REBCO samples whilst they're cold. So one of the first jobs I had was to design and build some apparatus to perform these experiments, given that no such thing existed until now, of course. Luckily for me, though, thanks to some semiconductor work performed in the 90s, the Surrey University Ion Beam Centre already had a cryocooler that was modified so it could be assembled on the end of their 2 MeV beamline. Now, shown on the slide is the cryocooler as I received it, complete with its various bits, and the beamline mounting plate, and on the right hand side is a CAD model I built as a starting point for the design. Now the idea was that when both irradiation shields are assembled, there was access for a 5mm beam spot onto the sample stage, now whose temperature could be maintained as low as 15 Kelvin by the cryocooler. So based on this setup, I designed and built an experiment that could fit into the rather limited space available, and shown us some pictures illustrating bits of the eventual solution. Now, samples generally consisted of a 2mm or 4mm long narrow track of REBCO etched directly onto the exposed REBCO of a 4mm wide coated conductor, all of which was then mounted onto a metal-clad PCB using copper foil tape. The whole sample assembly was then clamped onto the sample stage through current and voltage contacts, we're going to talk about a bit later, using a brass plate to even out the pressure. As you imagine, the sample was extremely sensitive to overheating, especially as the flux flow resistance built up during a superconducting transition. So to avoid damaging the sample, transport currents were pulsed through the sample, generally on timescales less than 100 milliseconds, as even this short duration allowed the sample's voltage response to be measured. Obviously, temperature measurement is very important, so 2 silicon diode temperature sensors were added to allow the sample to be measured, sample temperature to be measured and controlled. Now, this control was achieved using a 20 ohm nichrome heater built by myself and assembled onto the low temperature irradiation shield, whose power output was PID controlled. Now, although this system was not the most manicured, it certainly was sufficient to obtain and maintain a sample temperature, given that the cooling power of the cold head varied slightly over time, and given the extra heat loads the experiment was subject to, for example, during current application to the sample or when the ion beam was turned on. So getting current to the sample required a certain amount of wiring, and I tried various combinations of wiring, but the solution shown was the one that worked the best. Now the current The current circuit essentially contained three systems, so the PCB current contacts, which I mentioned before, and the first and second stage wiring. Now, the PCB current contacts were made by cutting specially designed pieces of copper from a single sheet, soldering the wires that needed to be attached to each piece onto them, and then arroditing them all into that rough arrangement shown on the left to a bare PCB board, thus making the 4 points of a 4-point current resistance experiment. As to the wiring, the idea was to avoid excessive heating of the sample via conduction along the wires from room temperature. Hence, the wires need to be as long as possible. But it was found that during previous iterations of the wiring, that if the wires were also too thin, significant ohmic heat dissipation in the wiring would lead to a measurable change in the sample temperature. Hence, the eventual solution was limited by the volume of the vacuum vessel itself, with the second and first stage wiring being fabricated from 2 mm diameter single core copper wire, each stage of which being about 180 centimeters long, and joined via a heat sink attached to the first stage current surface, shown here. Now, this was the best solution given that there was no equivalent space at the sample stage. So with everything assembled, IV curves could be assembled themselves by collecting together all the various voltage responses from several pulses and then fitting the power law expression to the data. Now shown is an example taken from a 2 mm long, 42 micron wide track measured whilst being controlled at 40 Kelvin. A maximum voltage was limited to 35 microvolts. Now, due to previous tests, this one was started at 10 amps and eventually went over voltage at 17 amps. Now, the figure at the top left shows the progression of the whole test over the course of roughly 10 minutes, and figures B through D are close-ups of various sets of pulses at different stages in the transition. All of these ones are added together to make the figure on the right showing the current versus voltage curve, with the power law fit IC value coming out to close to 14.4 amps. Now, this was equivalent to about 17 megaamps per centimeter squared, which, although was not very close to the expected value of 14 megaamps per centimeter squared, was reasonably close given the natural variation in JC along the length of a coated conductor, and that this experiment only really probed a tiny fraction of the whole coated conductor's REBCO volume. So given a series of these fits, the character of the self-field critical current versus temperature curve for the sample could be drawn and then compared with data supplied by the manufacturer given the measured track width, in this case measured by SEM imaging. Now, the temperature error bars shown on the graph on the left show the range of temperatures the sample was at during the transition, given that despite my best efforts there was heat flow through the sample and a non-zero thermal resistance between the sample and each temperature sensor. Now, although irradiating cold was the aim, I did do some room temperature irradiations experiments to provide a comparison. Now shown here is the IC versus temperature results for one of the 4 room temperature samples that I irradiated with 2 MeV helium. This particular sample was irradiated in stages up to 1.8 displacements per 1,000 atoms, hence the use of the kind of milli dPa unit. But others were irradiated as far as 4 milli dPa. This was roughly the displacement damage level shown by Fisher et al. In this paper that led to the low temperature high field properties of a supercoated conductor degrading even for their most capable sample. So needless to say, after all this work, I finally got some cold irradiation data back in December. It was very satisfying. I irradiated 2 samples over 2 days. Each was controlled at 40 Kelvin. And as shown on the right are the results from one of them with roughly where the different irradiations were. Essentially, it was 9 irradiations up to around 4 milli dPa, with the critical current at 40 Kelvin dropping off nearly linearly to begin with, and slowly leveling off as the damage built up, likely because further damage was being applied to previously damaged regions of the sample instead of pristine ones. Now all of the collected data allow me to plot irradiation response curves for the various sample properties at 40 Kelvin, which is shown here, which is the punchline of all my work. As mentioned before, the top left graph shows that TC for most samples drops roughly systematically, although it's much faster than the 3 Kelvin, drops systematically at about 5.5 Kelvin per millidPA, much faster than the 3 Kelvin per millidPA measured by Fisher et al. In response to fission neutrons. The most notable result, however, was not so much that the cold and the room temperature irradiated properties reduced proportionally with damage for all samples, but that when allowed to remain in room temperature air for a significant period, the cold irradiated sample properties improved significantly. That's this here, it's there, and it's there, compared to the equivalent experiment done at room temperature. Now, exactly why this is still needs a bit of investigating, but I think it's an interesting result given the implications for fusion tokamak magnets. So on that note, I'd just like to end my presentation. Many thanks for your attention, especially given what time it is here, and please let me know if you have any questions.